Hello, in this lecture we'll find out the area of the green shape using two different methods. In the drawing we have two circles. Each circle is passing through the center of the other circle, and we want to find out the area of this green shape. Okay, so we'll start with the first method, but before that I will explain to you what is sector. Sector is the area that is bounded by two radiuses and the arc that is between those two radiuses. Okay, so this green shape is a sector that is bounded by the radius AO, the radius OB, and the arc AB. And the angle between those two radiuses is equal to 60 degrees, but the sector can be with any other angle, and the area of a sector is equal to pi r square, when r is the radius of the circle, times the angle that is between those two radiuses. In this case is 60 degrees. 60 degrees over 360 degrees. Again, the area of sector AOB in the green shape, the green color, equals to pi r square times 60 degrees over 360 degrees. Okay? And we have another term that is actually segment. Segment is the area that is bounded by arc AB and chord AB. Okay? This green shape is the segment that is bounded by arc AB and chord AB that is attached to this arc. Okay? The area that is bounded by chord AB and arc AB is defined as a segment, and the formula for the area of this segment is actually the area of segment AB equals to the area of sector AOB minus the area of triangle AOB. Again, the area of sector AOB minus the area of triangle AOB equals to sector AB. The shape in the green color. Okay? So we will define the center of this circle as point P. This point is the center of this circle, and we will define it as point P. We will define the center of this circle as point Q. We will define the first intersection point between those two circles as point A, and we will define the second intersection point between those two circles as point B. Here we know that the radius of each circle is equal to 5 units. The radius of this circle is 5 units, and the radius of this circle is also equal to 5 units. In the next step, we will join together points P and B by a straight line. So here, line segment PB is the radius of this circle because of the fact that it starts from the center of the circle and ends at point B, that is a point on the circle itself. Therefore, PB equals to the radius of this circle, that is to say it equals to 5 units. Likewise, we will join points Q and B together by a straight line. And line segment QB is the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point Q, and ends at point B, that is a point on this circle itself. Therefore, it is the radius of this circle, that is to say it equals to 5 units. We will join points A and P together by a straight line. Again, line segment AP is the radius of this circle because of the fact that it starts from the center of this circle and ends at point A, that is a point of this circle itself. Therefore, it is the radius of this circle, that is to say it equals to 5 units. We join points A and Q together by a straight line. And line segment AQ is the radius of this circle because of the line segment AQ is the radius of this circle because of the fact that it starts from point Q, that is the center of this circle, and ends at point A, that is a point on this circle itself. Therefore, it is the radius of this circle, that is to say it equals to 5 units. So here, quadrilateral APBQ is a rhombus, and the definition of a rhombus is any quadrilateral that has 4 equal sides is defined as a rhombus. So here we can see in the drawing that rhombus APBQ has 4 equal sides. All of its sides is equal to 5 units. So you can write down that quadrilateral APBQ is a rhombus quadrilateral APBQ is a rhombus in the next step. We'll join points A and B together by a straight line. So here, line segment AB is the first diagonal of rhombus APBQ, and we'll join points P and Q together by a straight line. So here, PQ is also the diagonal of this rhombus APBQ. We will define the intersection point between diagonal AB and diagonal PQ as point M. And we have two characteristics of diagonals of a rhombus. I will write them down. the two characteristics of the diagonals of a rhombus the first characteristics of the diagonals of a rhombus is that they are perpendicular to each other the diagonals are perpendicular to each other so in our drawing diagonal AB is perpendicular to diagonal PQ and diagonal PQ is perpendicular to diagonal AB. That is to say, all the four angles are right angles and the second characteristic of the diagonals of a rhombus is that they bisect each other. Okay, the diagonals of a rhombus bisect each other. So here in our drawing, the diagonal AB bisects diagonal PQ, that is to say PM is equal to MQ, PM equals to MQ, but PQ is the radius of this circle, that is to say it equals to 5 units, so PQ equals to 5 units as a radius of this circle because of the fact that it starts from point P, that is the center of the circle, and then at point Q, that is a point on this circle itself. Therefore, PQ is the radius of this circle, that is to say it equals to 5 units. And again, PM equals to MQ. So if PM equals to X, then PQ will be also equal to X, or PM equals to X, then MQ will be also equal to X because of the fact that PM equals to MQ. And we also know that the diagonal PQ bisects diagonal AB, that is to say AM equals to MB. AM equals to MB because of the fact that the diagonal PQ bisects diagonal AB, it means that AM equals to MB. AM equals to MB and PM equals to MQ. So here X plus X equals to PQ, X plus X equals to PQ, x plus x is 2x, 2x equals to PQ, but we have already found out that PQ is the radius of this circle, that is to say it equals to 5 units. So from this equation we will derive that 2x equals to 5. We will divide this equation by 2 and we'll get that x equals to 5 over 2 units. So here x equals to 5 over 2 units, so I will substitute x by 5 over 2. And here also x equals to 5 over 2 units. In the next step, we will focus on those 4 right triangles, the right triangle, triangle APM, the right triangle, triangle AQM, the right triangle, triangle BQM, and the right triangle, triangle BMP. On those 4 right triangles, we know that if we relate to those angles, angle APM, angle BPM, angle AQM, and angle BQM, in those 4 angles, we know that cosine of one of each angle in this triangle, cosine of angle APM will be equal to 5 over 2 over 5, and also cosine AQM equals to 5 over 2 over 5, and also cosine BQM will be equal to 5 over 2 over 5, and also cosine BPM will be equal to 5 over 2 over 5. So we can write down that in 4 triangles, triangle APM, the right triangle, triangle AQM, the right triangle, triangle BQM, and the right triangle, triangle PMB. On those 4 right triangles, the cosine of those 4 angles will be equal to 5 over 2 over 5. Again, in those 4 right triangles, cosine of those 4 angles will be equal to 5 over 2 over 5. Here 5 over 2 over 5 is equals to 5 over 5 times 2. And here 5 over 5 is 1. So it is, this expression equals to, in conclusion, to 1 over 2. So we actually found out that the cosine of those 4 angles equals to 1 over 2, and if cosine of any angle equals to 1 over 2, it means that that angle equals to 60 degrees. So we actually found out that all four angles, they are equal to 60 degrees. So this angle equals to 60 degrees, this angle equals to 60 degrees, this angle equals to 60 degrees, and this angle also equals to 60 degrees. Okay? And in the next step, we will focus on those two triangles, triangle APB and triangle AQB. Okay? I'll repeat again, we will focus on triangle APB and triangle AQB. And we will actually prove that those two triangles can go into each other. So why those two triangles can go into each other? First of all, we know that AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. Okay. AP equals to AQ equals to 5 units. We also know that PB equals to BQ equals to also 5 units. PB equals to BQ also equals to 5 units. PB equals to BQ equals to 5 units. And AB is a common side, it belongs to both triangles, so we can write down that AB equals to AB. It's a common side that belongs to both triangles. AB equals to AB is a common side that belongs to both triangles. AB equals to AB. So we actually proved that triangle APB congruent to triangle AQB. According to side rule. I'll repeat again. We actually proved that triangle APB congruent to triangle AQB according to side rule. We actually proved that all the sides of triangle APB congruent to all the sides of triangle AQB. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that the areas of those two triangles equal to each other. So therefore, the area of triangle APB, here the squared bracket is the sign for the area. If the sign is the sign for the area, it means the area of triangle APB is equal to the area of triangle AQB. Okay? So again, I write it here that the area of triangle APB is equal to the area of triangle AQB. In the next step, we will calculate what is the area of sector APB. The area of sector APB, the area of this sector APB so the area of sector APB will be equal to pi r square times 120 degrees over 360 degrees. I repeat again, the area of sector APB will be equal to pi r square times 120 degrees, that is 60 plus 60, 120 degrees over 360 degrees. Again, the area of sector APB equals to pi r square times 120 degrees over 360 degrees. That is to say, r equals to 5 units, so r square is 5 square, 5 square is 25. So here we'll get that it equals to 25 pi, and 120 degrees over 360 degrees is 1 over 3, so it is 25 pi over 3. So, in conclusion, the area of sector APB is equal to 25 pi over 3 square units. Likewise, we'll calculate the area of sector AQB. The area of sector AQB will be equal to pi r square over 120 degrees over 360 degrees. I repeat again, the area of sector AQB will be equal to pi r square times 120 degrees over 360 degrees, when r is the radius of this circle that equals to 5 units. So again, r equals to 5, so r square is 5 square, 5 square is 25. So we'll have here 25 pi, and 120 degrees over 360 degrees is 1 over 3. So we found out that the area of sector AQB equals to 25 pi over 3 square units. The area of sector AQB equals to 25 pi over 3 square units. exactly like the area of sector APB that is also equals to 25 pi over 3 square units. So from these two equations, we will from these two equations, we will from these two equations we will conclude that the area of sector AQB equals to the area of sector APB. Okay, the area of sector APB is equal to the area of sector AQB and we also found out that the area of triangle APB is equal to the area of triangle AQB. Okay? We have those two equations. The area of sector APB equals to the area of sector AQB, and the area of triangle APB is equal to the area of triangle AQB. Okay? What is the area of segment APB? The area of this shape that is like a semicircle, sector APB, this shape that is like a semicircle. So the area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. I will repeat again. The area of segment APB equals to the area of sector AQB minus the area of triangle AQB. We have already found out that the area of sector AQB equals to 25 pi over 3 square units, and the area of triangle AQB is equal to the area of triangle APB. So if we define the area of triangle AQB as x, then the area of triangle APB will be also equal to x. Okay? So the area of triangle AQB is equal to x. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus x. Okay? And what is the area of segment AQB? The area of this segment AQB that is like a semicircle. It is not a semicircle, but it is like a semicircle. The area of segment AQB will be equal to the area of sector APB minus the area of triangle APB. I repeat again, the area of segment AQB equals to the area of sector APB minus the area of triangle APB. But we have already found out that the area of sector APB equals to 25 pi over 3 square units, and according to our definition, the area of triangle APB, according to our definition, the area of triangle APB equals to x. So, in conclusion, we found out that the area of segment AQB also equals to 25 pi over 3 minus x, exactly like the area of segment APB. Therefore, from these two equations, we will conclude that the area of segment APB equals to the area of segment AQB. Okay, the area of segment APB equals to the area of segment AQB. Okay, the area of segment APB equals to the area of segment AQB. So we can actually multiply the area of segment APB by 2, and we get the area of the green shape because of the fact that those two areas are equal to each other. So we will take the area of segment APB multiplied by 2, and we get the area of the green shape. So the area, okay, so you can see here that segment APB plus the area of segment APB plus the area of segment AQB equals to 25 pi over 3 minus x plus 25 pi over 3 minus x. So therefore we can multiply the area of segment APB by 2, and we will get the area of the green shape. So the area of the green shape will be equal to 2 times the area of segment APB, that is actually 25 pi over 3 plus x. Okay, so the only thing that is left to find is to find out the value of x, that is the area of triangle APB, and or the area of triangle AQB. So we will find out the area of triangle APB. So we know that AM equals to MB. AM equals to MB because of the fact that the diagonal PQ bisects diagonal AB, therefore AM equals to MB. So if we define AM, if AM equals to H, then MB will be also equal to H. So here, if we focus on triangle APM, the right triangle, triangle APM, here sinus 60 degrees, will be equal to h over 5. Sinus 60 degrees equals to h over 5. I'll repeat again. In the right triangle, triangle APM, sinus 60 degrees equals to h over 5. Sinus 60 degrees is equal to 3 over 2. So I'll write it down. We will multiply this equation by 5, and we will get that 5 times square root of 3 over 2 equals to h. So h equals to 5 times square root of 3 over 2. So here h equals to 5 times square root of 3 over 2. And here also h equals to 5 times square root of 3 over 2. So AB equals to 2 times 5 times square root of 3 over 2. AB equals to 2 times 5 times square root of 3 over 2. AB equals to 2 times 5 times square root of 3 over 2. Here 2 over 2 is 1. So we found out that AB equals to 5 times square root of 3. AB equals to 5 times square root of 3. And the area of triangle APB equals to, so the area of triangle APB, that is actually equals to x, according to our definition, it will be equal to the base AB times the height, that is PM, over 2. I'll repeat again. The area of triangle APB equals to the base of the triangle, that is AB, times the height, that is PM, over 2. And we have already found out that AB equals to 5 times square root of 3, PM equals to 5 over 2, all divided by 2. So the area of triangle APB equals to 5 times 5 is 25, 25 times square root of 3, all divided by 2 times 2. So the area x, that equals to the area of triangle APB, equals to 25 times square root of 3 over 2 times 2 is 4. So we found out that x equals to the area of triangle APB, that equals to 25 times square root of 3 over 4 square units. And the area of the green shape equals to the area of the green shape equals to 2 times 25 pi over 3 plus x. 2 times 25 pi over 3 plus x, and we just right now found out that x equals to 25 times square root of 3 over 4. So the area of the green shape equals to this expression. So here we'll take 25 out of these two expressions as a common factor, and we get that it equals to 2 times 25 is a common factor. So what is left from 25 pi over 3 after we took from it 25 is a common factor? What is left? It is actually pi over 3 minus, it is actually minus, it is plus x. It is plus 25 pi over 4 and here 2 times 25 is 50 times pi over 3 plus 25 pi, it's actually, we took 25 as a common factor, so inside the brackets we left with square root of 3 over 4. Again, we took 25 as a common factor, so what is left from this expression after we took from it 25 as a common factor, what is left, it is actually square root of 3 over 4. So we actually found out that the area of the green shape equals to 50 times pi over 3 plus, it is actually square root of 3 over 4. So here it is actually the area of the green shape equals to 2 times 25 pi over 3 minus x. So it is minus x. Therefore, the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. So here the area of the green shape equals to 2 times 25 pi over 3 minus 25 square root of 3 over 4. So here it is minus. So here is 50 times pi over 3 minus square root of 3 over 4. And also here it is 50 times pi over 3 minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay? That is the area of the green shape according to the first method. 50 times pi over 3 minus square root of 3 over 4 square units. So we finished with the first method, and in the next step I will present to you how to find out the area of this green shape according to the second method. In the second method we will do the same construction. First of all, we will define the center of this circle as point P. We will define the center of this circle as point Q. We will define the first intersection point between those two circles as point A, and we will define the second intersection point of those two circles as point B. We join points P and B, points B and Q, points A and Q, and points A and P together by a straight line like we did in the first method. We know that all the line segments that we created here are equal to 5 units. They are the radiuses of those two circles. PQ is the radius of this circle, that is to say, it equals to 5 units. So we have here two equilateral triangles. Triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to each other. They are equal to 5 units, and all the angles inside an equilateral triangle, they are equal to 60 degrees. And triangle PBQ is also an equilateral triangle because of the fact that all of its sides are equal to each other. They are equal to 5 units. Therefore, all of its angles will be also equal to each other, and will be equal to 60 degrees. And the equilateral triangle APQ is congruent to the equilateral triangle PBQ according to side rule. I write it down. The equilateral triangle APQ is congruent to the equilateral triangle PBQ according to side rule. All the sides of triangle APQ congruent to all the sides of triangle PBQ. All the sides are equal to 5 units. Therefore, we can conclude from it, because of the fact that those two equilateral triangles congruent to each other, we will conclude from it that the area of triangle APQ is equal to the area of triangle PBQ. The area of triangle APQ is equal to the area of triangle PBQ. Okay, so actually the area of the green shape here will be equal to the area of those two triangles, but because of the fact that the area of those two triangles is equal to each other, the areas of those two triangles are equal to each other, therefore we'll multiply the area of triangle APQ by 2, and we'll get that the area of the green shape is equal to 2 times the area of triangle APQ, plus the area of segment AP plus the area of segment PB plus the area of segment AQ plus the area of segment BQ. I'll repeat again, the area of the green shape will be equal to 2 times the area of the equilateral triangle APQ plus the area of segment AP plus the area of segment PB plus the area of segment AQ plus the area of segment BQ. Okay? And what is the area of triangle APQ? Here we have already found out. Here we have the diagonal AB. We have already found out that AM equals to 5 times square root of 3 over 2 so the area of triangle APQ will be equal to the base of the triangle, that is PQ, that is actually equal to 5 units, times the height AM over 2. I'll repeat again. The area of triangle APQ equals to the base of the triangle, that is PQ, times the height, that is AM, over 2. Here it is also AM equals to MB, so it is 5 times square root of 3 over 2. So the area of triangle APQ equals to PQ, that is 5 units. This is 5 units, times AM, that is 5 times square root of 3 over 2. All divided by 2. Again, the area of triangle APQ equals to PQ, that is 5 units, times AM, that is 5 times square root of 3 over 2, all divided by 2. So here, 5 times 5 is 25, times square root of 3 over 2 times 2 is 4. So we found out that the area of triangle APQ equals to 25 times square root of 3 over 4 square units, and 2 times the area of triangle APQ will be equal to 2 times 25 times square root of 3 over 4 plus the area of segment AP. What is the area of segment AP? The area of segment AP the area of segment AP will be equal to the area of sector AQP minus the area of triangle AQP. I repeat again, the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. And the area of sector AQP, this sector will be equal to pi r square times 60 degrees over 360 degrees. I repeat again, the area of sector AQP equals to pi r square times 60 degrees over 360 degrees minus the area of triangle AQP. The area of triangle AQP equals to the area of triangle PPQ, and we have already found out that the area of triangle AQP equals to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment AP equals to r equals to 5 units, so r square is 25 pi, r square is 25, so it is 25 pi over 6 minus 25 square root of 3 over 4. So actually, in conclusion, we found out that the area of segment AP equals to 25 pi over 6 minus 25 square root of 3 over 4. And so I write it down. This 25 pi over 6 minus 25 times square root of 3 over 4. And what is the area of sector PB? The area of sector of segment PB. The area of segment PB the area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. I repeat again, the area of segment PB equals to the area of sector PQB minus the area of triangle PQB. What is the area of sector PQB? The area of sector PQB, this sector equals to pi r square times 60 degrees over 360 degrees. Pi r square times 60 degrees over 360 degrees. Again, the area of sector PQB equals to pi r square times 60 degrees over 360 degrees minus the area of triangle PQB. And we already found out that the area of triangle PQB equals to the area of triangle APQ. The area of triangle PQB equals to the area of triangle APQ, and the area of triangle APQ equals to 25 times square root of 3 over 4. So the area of triangle PQB will be equal also to 25 times square root of 3 over 4. In conclusion, we found out that the area of segment PB equals to 25 pi over 6, because r equals to 5, so r squared is 5 squared, 5 squared is 25. So here it is 25 pi over 6 minus 25 times square root of 3 over 4. Again, we found out that the area of segment PB equals to 25 pi over 6 minus 25 times square root of 3 over 4, exactly like the area of segment AP. That is also 25 times pi over 6 minus 25 times square root of 3 over 4. So we conclude that the area of segment AP equals to the area of segment PB Okay, so the area of segment AP equals to the area of segment PB. And if we continue to calculate the area of segment QB and the area of segment AQ, we'll get that they are equal also to the area of segment AP. Therefore, in order to find out the areas of the four segments AP, PB, QB, and AQ, we will just multiply the area of segment AP by 4, and we will get the area of the four segments AP, PB, QB, and AQ. So therefore, we get that the area of the green shape, equals to 2 times the area of triangle APQ that is actually equals to 2 times 25 times square root of 3 over 4 plus 4 times the area of segment AP and we have already found out that the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. So I'll repeat again. The area of the green shape equals to 2 times the area of triangle APQ plus 4 times the area of segment AP, because of the fact that the area of segment AP equals to the area of segment PB equals to the area of segment QB and equals to the area of segment AQ. We'll multiply the area of segment AP by 4, and in this way we'll get the areas of the four segments AP, PB, PQ, and AQ. So in conclusion, we found out that the area of the green shape equals to 2 times the area of triangle APQ. Why? Because triangle APQ can go into triangle PBQ. Therefore, they have also the same areas. So the area of those two triangles equals to the area of triangle APQ times 2, plus the area of the 4 segments. But because of the fact that all the 4 segments, they are equal to each other in their areas, we will multiply the area of segment AP by 4, and we will get the area of this green shape. That is actually 2 times the area of triangle APQ plus 4 times the area of triangle of 2 times the area of segment AP. Okay, the area of the green shape equals to 2 times the area of triangle APQ plus 4 times the area of segment AP. And the area of triangle APQ is 25 times square root of 3 over 4. So we multiply it by 2. And 4 times the area of segment AP. And the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. So we multiply it by 4, and we will get that the area of the green shape equals to 2 times 25 is 50 times square root of 3 over 4 plus 4 times 25 is 100. So we get here 100 pi over 6 minus 4 times 25 is 100 times square root of 3 over 4. So here we have 50 times square root of 3 over 4 minus 100 times square root of 3 over 4. It equals to minus 50 times square root of 3 over 4. And there we have 100 over 6 pi. We divide both the numerator and the denominator by 2, and we get that 100 over 2 is 50. So it is 50 pi, and 6 over 2 is 3. Okay, so here we will take 50 as a common factor out of those 3 expressions, and we will get that the area of the green shape equals to 50. So here we took 50 as a common factor. So what is left from these expressions after we took from it 50 as a common factor? What is left, it is actually pi over 3 minus, here we took 50 as a common factor. What is left from this expression after we took from it 50 as a common factor? What is left, it is actually square root of 3 over 4. So in conclusion, we found out that according to the second method, the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. In both methods, we found out that the area of the green shape indeed equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay, so in the next step, I will summarize the lecture. Actually, we wanted to find out the area of this green shape and here we have 2 circles. Each circle is passing through the center of the other circle. The radius of each circle, each circle is equal to 5 units, and we want to find out the area of this green shape. So first of all, I presented to you the definition of a sector. So here, a sector is the area that is bounded by 2 radiuses and the arc that is included between those 2 radiuses. So the green shape is sector AOB, and the area of this sector equals to pi r squared times 60 degrees over 360 degrees. Okay? So the area of a sector equals to pi r squared, that is r is the radius of the circle, times the angle that is between between the radiuses over 360 degrees. In this specific case, the angle between the two radiuses is 60 degrees, but the angle could be any other angle. So the area of a sector equals to pi r squared times the angle that is between the two radiuses over 360 degrees. Okay, and then I presented to you what is the area, what is the definition of a segment. The definition of a segment is the area that is bounded between the chord AB and the arc that is attached to this chord. Again, the area between the arc and the chord that is attached to that arc is defined as a segment. So here, the area of the screen shape, that is the area inside between the area that is bounded by arc AB and chord AB, is the area of the green shape that is actually equals to the area of sector AOB minus the area of triangle AOB. Again, the area of sector AOB minus the area of triangle AOB equals to the area of segment AB. Okay, so segment is the area that is bounded by chord, and the arc, or the arc and the chord that is attached to that arc is the area of a segment, or is this definition of a segment, and the area of the formula for the area of the segment is the area of sector AOB minus the area of triangle AOB. Okay, so the area that is bounded by an arc and the chord that is attached to that arc is a segment, and the formula for the area of segment is the area of sector AOB minus the area of triangle AOB. Okay, so this is the definition of a segment. Then we connected together points A and P, points A and Q, points B and Q, and points P and B by a straight line. Here, for example, PB is the radius of this circle. Why? Because it starts from the center of the circle and ends at point B, that is a point on this circle itself. Therefore, PB is the radius of this circle, that is to say it equals to 5 units. And in the same way, we find out that all the 4 line segments are also the radiuses of those circles, therefore they are equal to 5 units. And by drawing those 4 line segments, we created a rhombus. A rhombus is a quadrilateral that all of its 4 sides are equal to each other. So actually here, quadrilateral APBQ is a rhombus. Then we join points A and B together by a straight line. AB is the first diagonal of rhombus APBQ. Then we join points P and Q together by a straight line. PQ is the second diagonal of rhombus APBQ. And we have 2 characteristics for the diagonals of rhombus. The first characteristics of diagonals of a rhombus is that they are perpendicular to each other. That is to say, diagonal AB is perpendicular to diagonal PQ, and diagonal PQ is perpendicular to diagonal AB. Therefore, all four angles here are right angles. And the second characteristic of the diagonals of a rhombus is that they bisect each other. That is to say, diagonal AB bisect PQ, that is to say, PM equals to MQ, and diagonal PQ bisect diagonal AB, that is to say, AM equals to MB. AM equals to MB. So because of the fact that PM equals to MQ, we will define PM as X, therefore MQ will be also equal to X. So actually PQ will be equal to PM plus MQ, that is to say PM is X and MQ is X. So PQ will be equal to X plus X, but PQ equals to 5 units because it is the radius of this circle. PQ is the radius of this circle, it equals to 5 units. So we got that 2x equals to 5. We divided this equation by 2 and we got that x equals to 5 over 2. That is to say PM equals to 5 over 2 and MQ also equals to 5 over 2 because they are equal to x, and x equals to 5 over 2. So then in the next step we focused on the four right triangles, the right triangle AQM, the right triangle APM, the right triangle PBPM, the right triangle MBQ, and we focused on those angles, those four angles. In those four angles we can write down that cosine of those four angles on those four triangles in the right triangle APM, the right triangle AQM, the right triangle PBQM, and the right triangle PMB. We know that cosine of those four angles will be equal to 5 over 2 over 5. The cosine of any of the four angles will be equal to 5 over 2 over 5. That is to say 5 over 2 over 5 is 1 over 2. So we got that cosine of any of those four angles will be equal to 1 over 2. That is to say the angle, all four angles are equal to 60 degrees. So we found out that all four angles here are equal to 60 degrees. Then we proved that those two triangles can go into each other. Why those two triangles can go into each other? First of all, we know that AP equals to AQ equals to 5 units, AP equals to AQ equals to 5 units, PB equals to QB equals to 5 units also, PB equals to BQ equals to 5 units, and AB equals to AB. AB is a common side, it belongs to both triangles, so AB equals to itself. It's a common side. So we actually proved that all four sides in triangle APB can go into all the four sides, all the three sides. All sides in triangle APB can go into all three sides of triangle AQB. Therefore, those two triangles can go into each other according to side rule. We actually proved that triangle APB, this is the sign of congruent. Triangle APB can go into triangle AQB according to side rule. And from the fact that those two triangles can go into each other, we will conclude that they have also the same areas. So the area of triangle APB is equal to the area of triangle AQB. Okay? So the area of triangle APB is equal to the area of triangle AQB. What is the area of sector APB? The area of sector APB, this shape that is like a semicircle but is not a semicircle, the area of sector APB, this the shape that is like an half circle, it will be equal to the area of sector AQB minus the area of triangle AQB. So the area of sector APB, no, the area of sector APB, it is actually the area of this sector, sector APB. It will be equal to pi r squared times 120 degrees over 360 degrees. The area of sector APB equals to pi r squared times 120 degrees over 360 degrees. So this is actually sector APB. Okay, this is sector APB, and the area of sector APB equals to pi r squared times 120 degrees over 360 degrees. And r equals to 5. Therefore, r squared is 5 squared, 5 squared is 25. So the area of sector APB will be equal to 25 pi 120 degrees over 360 degrees is 1 over 3. So in conclusion, we found out that the area of sector APB equals to 25 pi over 3 square units. Then we calculated the area of sector AQB. The area of this sector AQB, it will be equal to pi r squared times 120 degrees over 360 degrees. The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. R equals to 5, so r squared is 25, so we have here 25 pi times 120 degrees over 360 degrees is 1 over 3. So in conclusion, we found out that the area of sector AQB also equals to 25 pi over 3. So the area of sector APB is equal to the area of sector AQB, and we already found out that the area of triangle APB is equal to the area of triangle AQB. We define the area of those two triangles as x. So the area of triangle AQB equals to x, and the area of triangle APB also equals to x, according to our definition. And what is the area of segment APB? The area of segment APB, this shape that is like a semicircle but is not a semicircle, the area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. So the area of segment APB equals to the area of sector AQB minus the area of triangle AQB. And the area of sector AQB, we already found out that it equals to 25 pi over 3. And the area of triangle AQB equals to x according to our definition. Then we calculated the area of segment AQB, the area of this segment AQB that is similar to a semicircle but it is not a semicircle. The area of segment AQB will be equal to the area of sector APB minus the area of triangle APB. The area of segment AQB equals to the area of sector APB minus the area of triangle APB. And we already found out that the area of sector APB equals to 25 pi over 3, and the area of triangle APB equals to x according to our definition. So we actually found out that the area of segment AQB is equal to the area of segment APB. Okay, they both equals to 25 pi over 3 minus x square units. The area of segment APB equals to the area of segment AQB. Therefore, the area of the green shape will be equal to the area of sector APB times 2 because of the fact that the area of sector APB, the area of segment APB equals to the area of segment AQB. Therefore, we will multiply the area of one of the segments by 2 and we will get the area of the green shape because of the fact that we have here two halves. So if we multiply one half by 2, we will get the area of the green shape. Okay, so the area of segment APB that equals to 25 pi over 3 minus x times 2 will be equal to the area of the green shape. Okay? So we have to find out the value of x. We have to find out the value of x, and x is the area of triangle APB according to our definition, and the area of triangle APB will be equal to the base of the triangle that is AB times the height that is PM over 2. So x is the area of triangle APB, and it equals to the base of the triangle that is AB times the height that is PM over 2. And what is the value of AB? The value of AB equals to, here, if we focus on this one of the triangles, triangle APM, here we know that sinus 60 degrees equals to AM over 5. Sinus 60 degrees equals to AM, that is age, over 5. We know that sinus 60 degrees is square root of 3 over 2. So we multiply this equation by 5, and we found out that h equals to square root of 3 over 2 times 5. But AB equals to 2 times h. It is h plus h. So we have to multiply h by 2. We multiplied h by 2, and we got that AB equals to 2 over 2 is 1, so AB equals to 5 over 5 times square root of 3. AB equals to 5 times square root of 3. So here, the area of triangle APB that is actually equals to x equals to AB that is 5 times square root of 3 times the height that is PM that equals to 5 over 2 over 2. So here, 5 times 5 is 25, so it is in the numerator we have 25 times square root of 3. In the denominator we have 2 times 2. So in conclusion, we found out that x that equals to the area of triangle APB equals to 25 times square root of 3 over 2 times 2 is 4. So it is 25 times square root of 3 over 4 square units. This is the value of x, and so the green area equals to 2 times the area of segment PB, or of segment APB, and the area of segment APB, the area of segment APB equals to 25 pi over 3 minus x. So it equals to 25 pi over 3, and x, we have already found out that x, that is the area of triangle APB, equals to 25 times square root of 3 over 4. So 2 times the area of segment APB will be equal to the area of the green shape. So here we took 25 as a common factor of this, out of these two expressions, and we got that the green area, the green shape equals to 2 times 25 times pi over 3 minus 25 times square root of 3 over 4. 2 times 25 is 50. So we got that the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay? Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we did the same construction as the first method. And here we have two equilateral triangles. Triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to 5 units, and triangle PBQ also is an equilateral triangle, all of its sides are equal to 5 units. Those two triangles can go into each other according to side rule. Therefore, triangle APQ is the same area of triangle PBQ because of the fact they can go into each other, therefore they have the same areas. So triangle APQ is the same area of triangle PBQ. Okay, so the area of the green shape will be equal to 2 times the area of triangle APQ plus the areas of the 4 segments, segment AP, segment PB, segment BQ, and segment AQ. So the area of the green shape will be equal to 2 times the area of triangle APQ plus the area of segment AP plus the area of segment PB plus the area of segment AQ plus the area of segment BQ. And what is the area of triangle APQ? The area of triangle APQ, the area of triangle APQ equals to PQ times AM over 2. It equals to the base of the triangle times the height over 2. So it equals to the base PQ times the height AM over 2. PQ equals to 5. AM equals to 5 times square root of 3 over 2. We already found out in the first method. All divided by 2. 5 times 5 is 25. 25 times square root of 3 over 2 times 2 is 4. So we found out that the area of triangle APQ equals to 25 times square root of 3 over 4. So 2 times the area of triangle APQ, it equals to 2 times 25 times square root of 3 over 4 plus the area of segment AP. What is the area of segment AP? The area of segment AP equals to the area of sector AQP minus the area of triangle AQP. The area of sector, the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. The area of sector AQP equals to pi r squared times 60 degrees over 360 degrees, r equals to 5 units. And the area of triangle AQP, we have already found out that the area of triangle AQP equals to 25 times square root of 3 over 4. R equals to 5, so r squared is 25, so in the numerator we have 25 pi, and 60 degrees over 360 degrees is 1 over 6. So the area of sector AQP equals to 25 pi over 6 minus the area of triangle AQP, that is actually 25 times square root of 3 over 4. So the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. Then we found out the area of segment PB. What is the area of segment PB? The area of segment PB will be equal to the area of sector BQP minus the area of triangle BQP. Again, the area of segment PB equals to the area of sector PQB minus the area of triangle PQB. And the area of sector PQB equals to pi r squared times 60 degrees over 360 degrees. And the area of triangle PQB is equal to the area of triangle PQA. Here, the area of triangle PQA equals to the area of triangle PQB. Therefore, the area of triangle PQB will be equal to 25 times square root of 3 over 4. So in conclusion, we found out that the area of segment PB is equal to the area of segment PA. Okay, the area of segment PA equals to the area of segment PB. And if we continue to calculate the area of the segments, we will find out that the areas of all the segments, they are equal to each other. So we will take one segment, multiply it by 4, and in this way we will get the area of the 4 segments. Okay? So we did it. Here the area of the green shape equals to 2 times the area of triangle APQ plus 4 times the area of segment AP. Why? Because of the fact that all the segments, they are equal in their areas. So if we multiply the area of one segment by 4, we will get the area of the 4 segments in total. So the area of the green shape equals to 2 times the area of triangle APQ, because of the fact that those two triangles have the same areas, plus the area of the 4 segments, and the area of the 4 segments equals to 4 times the area of segment AP. Okay, so the area of triangle APQ equals to 25 times square root of 3 over 4, so 2 times the area of triangle APQ equals to 2 times 25 times square root of 3 over 4, plus 4 times the area of segment AP. The area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. So here 2 times 25 is 50. So we got here this expression equals to 50 times square root of 3 over 4. 4 times 25 is 100. So here we have 100 pi over 6. 4 times 25 is 100. So we have here minus square root of 3 over 4. 50 square root of 3 over 4 minus 100 square root of 3 over 4 is minus 50 square root of 3 over 4. And here we divided both the numerator and the denominator by 2, and we got that 100 over 100 over 2 is 50. 6 over 2 is 3. So in conclusion, we found out that the area of triangle of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we took 50 as a common factor out of these two expressions, and what is left from this expression after we took from it 50 as a common factor, what is left, it is actually pi over 3, and what is left from this expression after we took from it 50 as a common factor, what is left, it is actually square root of 3 over 4. So we found out that the area of the green shape according to the second method equals to 50 times pi over 3 minus square root of 3 over 4 square units, and it is exactly the same result that we got in the first method. Okay, so the area of the green shape in both methods, we found that it is equal to 50 times pi over 3 minus square root of 3 over 4 square units. Okay, thank you very much.